A very good morning and welcome back. So, in our class today, we will start with analysis of coupled circuit or circuits which actually involves what we call as mutual inductance. Mutual inductance. Just to start with, let us consider an example of a coupled circuit. Let us say you have a battery, you have a switch, a resistance, a capacitance here, another resistance, and inductance. Okay, this is one circuit there, and on the right hand side there is another circuit. So this is can be considered as an example of coupled circuit. Why a coupled circuit? Because here this coil, which is let me call as coil 1, and this coil, let me call this one as coil 2, are placed in the vicinity of each other, and because of that placement the current or the conditions of coil 1 will affect the performance of coil 2. Okay, and when there is a mutual relationship between the two, what I'm saying is that the current that would flow through the coil 1 will actually affect the voltage that we'll see across coil 2, and the current which will flow across coil 2 will actually change the voltage across coil 1. So there is a mutual relationship between the two, and we can call that mutual relationship as uh, mutual inductance. So such a circuit we can call as coupled circuit, and it is not just that you have to place the coils in the vicinity of each other. It can be distant also, but the effect may reduce with distance. Okay, so first of all, we see that coupling may or may not happen at distant places, but in the vicinity, coupling is supposed to happen. Okay, and which type of coupling is this? When we place two coils near each other or in the vicinity of each other, the coupling or is a magnetic coupling. The coupling is a magnetic coupling, and you see that the voltage across this particular inductor will be affected only and only if there will be transients. Otherwise, I have already told you that inductor is nothing but a wire, and for DC conditions the voltage across an ideal wire should be zero, and the same should be true for coil also, because a coil is nothing but a geometrically modified wire, modified in such a way that magnetic fields are induced or flux is induced across this. Okay, so first of all, you understand that such a thing like mutual inductance or coupling is only and only possible where switching transients occurs. Okay, it is possible only in the circuit where switching transients occur, or you can also say that such coupling or the mutual coupling is also possible in the circuits in which we have time varying signals. If we have a circuit and have time varying signal, then also you could have to apply the concept of mutual inductances. So for AC or time varying signals, we will have to apply the analysis of coupled circuit or mutually coupled circuits. Fine. Now, consider that a very typical example you have seen as a diagram. Actually, this concept of mutual inductance comes into play only and only when you have two coils placed in the vicinity of each other. Okay. For example, let me coil this as coil 1 and this as coil 2. The effect of mutual inductances will come into play only and only if they are placed in the vicinity of each other. Now, let us suppose that we have a network N. So, N is a network and N is containing sources which changes with time. So, all sources change with time in the given network N. Fine. And we can consider that changing values of parameters. For example, let's say if we have two such coils, so we have V1, we have V2, which would be changing with time. You can also have I1 and we can also have I2, which would be changing with time. And you know that for a simple inductor which is having value L, a simple inductor which is having value L, and the current I flows through it, okay, and that current is not a constant current, it changes with time, then the voltage across this mutual inductance, we can say that is equals to V equals L di by dt. Okay, it is equals to L di by dt, which is L di by dt. Fine. Or if you talk in terms of the EMF induced, we can call that as, because the induced EMF have the opposite the effect to what is the causal agent. So current is the causing agent. So therefore E would be negative of the value of current. Okay. But if we are not interested in the EMF, we are only interested in the voltage values, then we can consider it to be LDI by dt. But remember that such a thing is happening when the current which is flowing through the same coil, the current I1, let me call this as, let's say, I1, and this is L1. So this is happening when the same current is flowing through L1. It is not the current of some other inductance. Therefore, we call L1 as self-inductance. Okay. Actually, it comes from phi is equals to Li, and we can use that. So from there, I hope you remember, from phi equals to Li, we get that d phi by dt has to be equals to Ldi by dt. Remember now, because I is not constant, so I should not be using a capital sign for it. It is a general convention that if things are AC or time varying, then I should use a small letter for it. So d phi by dt is a change in flux with respect to time, and you know that it is nothing but equals to change in the EMF with a negative sign. Or if you consider voltage, you can take that to be positive. But remember over here that this L is the property of the same coil over there. L is the property of the same coil over there, because I1 is a current flowing through L1. This is the concept of mutual inductance. Okay. Similarly, if you have over here coil 2, and let's say I2 is a current that flows through it, I1 is a current that was flowing through it, this is V2 and this is V1, then in that case, if this second coil would not have been present there, then you understand and you know that we could have taken for this particular thing, um, it's simple, V2 is equals to LDI2 by dt. Fine. So this L over here is now, if let me call this as L2, this L2 is a self inductance, not the mutual inductance. Okay. So I1 and I2 are the current which are changing with time and therefore causing changing fluxes phi1 and phi2. So when I1 flows through it, but you know that I1 is varying with time, then we can say that because of this time varying current, a time varying flux will be introduced. Fine. So I1 which is changing with time, or I2 which is changing with time, actually causes a time varying flux phi1 and phi2. Fine. So I hope you must have remember, or you must remember that particular case in which we used to study in our 12th class, that for example, it is called as a BH curve. Okay. So here you have H, it means the applied magnetic field, and here you have B, which is the uh, induced magnetic field. So we can call it as a field or intensity of magnetization, and on the other hand we have the magnetic field applied. Therefore, in such cases, it is, more or less you sometimes get a hysteresis type of a thing. Okay. But for a very small span of this particular case, you can consider it to be a linear response for a very small range. Okay, let us consider that to be a linear response, because ऐसा ही हमें पढ़ाया भी जाता है कि that पहले ये linearly बढ़ेगा, then it will saturate, and then if you start to reverse the field, it will not come back. We call that as coercivity and retentivity. So I hope you remember all that. But remember one thing: in this particular curve, this h is actually uh, proportional to the current flowing through the circuit, and this b is directly proportional to your flux induced. Okay. So in a way, because our magnetic field intensity is proportional to current, and the induced magnetic fields is proportional to the flux, or the flux induced, so there is a direct relationship between this phi and this I, and we call that as phi equals Li. From here we can, okay. Now, because now you understand that if current flows in a particular circuit, then the magnetic field is induced. Now we come to the concept of mutual inductances. Okay, I will tell you why these mutual inductances are important. Consider two coils placed near each other. This is coil 1, this is coil 2, let's say. Okay, so we have coil 1 and we have coil 2. And let us say that in coil 1, the number of turns which I have taken in, the number of coil turns is equals to N1, and number of coil 2 has a N2 number of turns. Okay, so coil 2 is having N2 turns, coil 1 is having N1 turns only. Now, let's say a time varying current I1 is flowing through this. If I1 is flowing through this, then what will happen? I'm actually not going to show you the sign, but a magnetic field will be induced around this. So if current is flowing like this, it is flowing in some way, and you know that some magnetic field will be induced. Okay, so there will be a magnetic field around it. So this is what I'm drawing is the direction of magnetic field lines or magnetic fields. Okay, so because you know that magnetic field uh, is a non-contact force, therefore it happens in a particular field. It can happen without any contact, but you have to come near the uh, point where a magnetic is placed in order to feel its presence. Okay, so because I1 which is flowing through this coil current I2, a flux is induced, and that flux let me call as phi1. If a time varying current flowing through a coil, a flux is induced, and I'm calling that as phi1. Now this phi1, which is the total flux, which is the total flux passing through the coil 1, can also be written as two different type of flux. It is equals to, I can write it as two different type of flux. It is equals to, first, the flux which passes only through phi 1 or only through coil 1. So see that इनमें से कुछ फील्ड लाइंस ऐसी हैं जो केवल कॉइल 1 में पास होती है, कॉइल 2 में पास नहीं होती है. तो यू सी there will be many such lines, but there are few lines which passes only through coil 1 and not through coil 2. We can call that flux as phi 11. Okay, we can call that flux as phi 11, and technically it is it is said that phi 1 is a flux which cuts coil 1 only. Phi 1 is a flux which cuts coil 1 only. Okay. So this only is important over there. Now I can write, because it is not the total. If I take only those flux line which is passing through coil 1 only, not in coil 2, it is not the complete definition of phi 1 or complete numerical equivalent of phi 1, because I should also consider some of the lines which are passing through phi 2 also. Okay. So I should also consider phi 1 2. So this is phi 1 2, and phi 1 2 is what? Phi 1 2 are the flux line which cuts both coil 1 and coil 2. Both coil 1 and coil 2. This is the phi 1 2. Okay. So phi 1 cuts only 1, 2 को cut नहीं करते हैं, and phi 1 2 cut both coil 1 and coil 2. You see. Now we can write that the sum of those flux which passes through only coil 1 and through coil 1 and coil 2 is a total flux across coil 1. So phi 1 then is the flux which cuts coil 1. अब देखिए यहाँ पे only नहीं लगा है, इसलिए ये important चीज है. And you know that phi 1 is a total flux across coil 1, जो कि बाहर देखें तो दो तरीके का हो सकता है. एक ऐसी लाइन, एक ऐसा पोर्शन जो केवल कॉइल 1 से पास होता है, और एक ऐसा पोर्शन जो कॉइल 1 और कॉइल 2 दोनों से पास हो सकता है. एंड दैट्स व्हाई वी हैव रिटन phi 1 is equals to phi 1 1 plus phi 1 2. Okay. Similarly, you can also have the same thing happening for this case. So now you have I2 flowing. We are not considering the effect of I1 now. We are saying that I2 is flowing through the coil 2. And in this case, you see that there would be an EMF induced, and I can call that as total flux phi 2. And you know that that total flux phi 2 will be comprising of two parts. First, the flux which is passing only through phi 2, like this one, जो केवल दूसरे कॉइल में ना जा पाए, एयर में ही रह जाए, उसे हम कहेंगे इट इज ओनली थ्रू कॉइल 2, प्लस flux which is going in both coil 2 and coil 1. So I have phi 2 1 and phi 2 2 like this with me. So phi 2 cuts coil 2, phi 2 1 cuts coil 1 and 2 both, and phi 2 2 cuts coil 2 only. Okay. Now, uh, as you know that, because the voltage induced depends on number of turns into d phi by dt also. I hope you remember this thing. V1 is equals to N1 d phi 1 by dt. It was because of the self inductance. So total voltage across the coil 1 would be dependent on the number of turns across coil 1 and the total flux across coil 1. Similarly, V2 would be N2 d phi 2 by dt. Okay. The total voltage across coil 2 will be dependent on the number of turns in coil 2 and the flux induced. Fine. But this portion is a very small portion. This portion is a very small portion because you're not considering the effect of mutual inductances as of now. You're not considering the effect of current I2 on the voltage I1 or voltage V1, or you are not checking the effect of current I1 on voltage V2. But that is to be considered, and that is whole about the concept of mutual inductances. Okay. So over here till this point we only have introduced a definition of self inductance, but mutual inductance is also playing a big role in it. Fine. So let me call that actually, you know that the total flux now that would be passing through coil 1, the total flux that would be passing through coil 1 first is phi 1. that we know, which is because of its own current I1. तो phi 1 तो total हो गया. This is a phi 1 total flux which is caused by I1. So this phi 1 is total caused by I1. But there is some portion which is induced or introduced by flow of I2 as well. So this phi 1 is not the complete flux. When I2 will flow, there will be another portion which we can call as phi 21 that will add on to the voltage V1. Okay, so phi 21 will also add to the voltage V1 in a particular way. So now let us consider what is going to be the total flux across it. So you have to take phi 1 and you also have to take phi 21. You have to take phi 1 and phi 21 because दोनों करंट्स का इफेक्ट अगर हमें स्टडी करना है देन वी हैव टू टेक इट. अगर केवल आप phi 1 देखेंगे देन यू कैन डील विद सेल्फ इंडक्टेंसेस, but because you have to deal with mutual inductance, therefore you also have to consider phi 21. Fine. So we can say that the total flux that passes through coil 1 because of all currents. Okay. So the total flux which will pass through the total flux through coil 1, the total flux that will pass through coil 1 will actually be phi 1 plus some portion introduced by source 2 or I2. So this is my total flux. Okay. And I can now multiply it with the number of turns in the coil. So that is N1 turns in the coil. Okay. And now I can take the derivative of it. So the voltage which I would see across V1 will be actually dependent on N1 d phi 1 by dt plus N1 d phi 21 by dt. Why this N1 is there? Because although the field lines are there because of I2, but they are cutting your coil 1. Therefore, we need to consider N1 and not N2. And this happens over here. This phi 21 is because of I2. This phi 21 is because of I2. And this phi 1 is because of I1. Okay. This phi 21 is because of I2 and this phi 1 is because of I1. So in a way, we can say that you know that it's the same thing we can replace with Li also, because I have told you, because H is equals to N into I actually. Okay. Uh, in the graph earlier, I told you that H is proportional to where it is. Uh, yeah, in this particular graph, I told you that H is proportional to I, but this is actually equals to H equals Ni. Okay. So H is actually equals to number of turns in the coil multiplied with I. Therefore, I can just replace such things with V1 is equals to self inductance. तो देखो I1 और I1 का ही इफेक्ट है, तो it is L d I1 by dt. So from here, how we come here is because of the relationship between the H and B curve. That's it. You just remember that. Okay. And we from now on will not be writing anything about N and phi. We will only be dealing with current and inductances. Plus M12, let me call this as a special case, M12. This is also an inductance, di2 by dt. Okay. As of now, although I have just written it as positive, but it may be positive or negative. So this sign can be additive or subtractive depending on a special thing. Okay. This plus sign can also be a minus sign. It is possible that the direction of flux in one coil may be opposite to the direction of field lines in the second coil, and therefore instead of adding on to the voltage, it reduces the voltage. How to decide that, कैसे समझ आएगा कि प्लस लगेगा या माइनस लगेगा, that is a different thing. That is a thing to be covered in the next part. Okay. But as of now, you understand that in V1, there is one portion which depends on self-inductance. And there is another portion which depends on what we call as mutual inductance. Okay, mutual inductance. And this is M12, which is saying that the contribution in the voltage V1 because of the current I2. Okay, the contribution in the voltage V1 because of the current I2. On the similar note, you can write for V2 that your V2 will actually be equals to N2 d phi 2 by dt plus N2 d phi 1 2 by dt. So here it was 2 1, here it is 1 2 because the source is 1. So the current, this phi 1 2 is because of current I1 now. So I can simply write it in terms of self inductance that it is equals to L2 d phi 2 by dt plus minus, we don't know about this sign yet, some M1 2, or you can call it as M21 di1 by dt. Okay, M21 di1 by dt, where L1, L2, and usually people consider that M21 is equals to M12. There is a mutually equal effect, like the effect on 1 on 2 and 2 on 1 is same, and this is what people practically consider, that the mutual inductance effect of one on another should be same. Therefore they call it as just M. So actually M12 और M21 दोनों को सेम मानते हुए M कंसीडर करते हैं. तो हमारे पास जो पैरामीटर्स हुए या जिसे हम सर्किट पैरामीटर्स बोलते हैं वो हुए तीन फॉर अ टू कॉइल सिस्टम. एक हुआ कॉइल 1 का सेल्फ इंडक्टेंस, एक हुआ कॉइल 2 का सेल्फ इंडक्टेंस, और एक हुआ इन दोनों के बीच में रिलेशनशिप की वजह से म्यूचुअल इंडक्टेंस. वैसे तो हम चार कंसीडर कर रहे हैं M1 to M21, but practically you will consider that because the effect of one on the other should be same, therefore the self inductance should be L1 L2 and the mutual inductance should be M. Now the main task is how to decide this sign, whether it will be positive or negative. Okay, actually it depends on what is called as the current and the winding direction. अब वाइंडिंग किस चीज की, आपने देखा हो जो कॉइल्स होते हैं वो एक तरीके से ऐसे वाइंडेड होते हैं. वाइंडेड मतलब एक चीज के ऊपर लपेटे हुए गए होते हैं. तो वो वाइंडिंग का डायरेक्शन क्लॉकवाइज है या एंटी क्लॉकवाइज है, उस वाइंडिंग का डायरेक्शन क्लॉकवाइज है या एंटी क्लॉकवाइज है. मान लीजिए कॉइल 1 वाज क्लॉकवाइज, कॉइल 2 वाज एंटी क्लॉकवाइज, तो इस चीज को डिसाइड करना पड़ता है. दैट थिंग इज द एक्चुअली गवर्निंग थिंग व्हिच वुड डिसाइड वेदर देयर वुड बी अ पॉजिटिव साइन और अ नेगेटिव साइन इन बिटवीन. Done. And that particular thing is what we call as dot convention. Dot convention. And this is the thing which we would cover in the next part of our lecture. Dot convention. Thank you so much.